So for today, we're going to talk about differential forms. And I'm going to start with defining what an alternating tensor is. I'll give some intuition for that, define it, and then we'll talk about how to integrate forms, and then we will define something that will make Stokes define differential forms in a way that makes Stokes' theorem true. Okay, so so first we're going to define what an alternating tensor is. So the intuition behind this is to find the volume of a parallelepiped or into the area of a parallelogram. So let's say I have two vectors, v1 and v2. I want to define some kind of function that takes v1 and v2 as inputs and outputs the area. Area of so if you would notice, so let's say we scale v2 by a factor of lambda. Let's say we scale it by lambda. Sorry, this is v2, and then we scale it. Let's say we scale it to lambda v2. You would notice that the area gets multiplied by lambda. So what we want is omega of v1 lambda v2. We want this to equal to lambda times omega of v1 v2. And then let's say you have another vector v3. Say this is v1, this is v2. And let's say you have v3. And the area of this larger parallelogram is the area of this plus the area of this, right? So you would want omega of v1 plus v3 comma v2 to be equal to omega of v1 comma v2 plus omega of v3 comma v2. So basically we require omega to be linear in each entry, right? Because we wanted to represent the area of a parallelogram. And then notice that if we switch v1 and v2, let's say I write v1 here, and v2, it shouldn't change the area, right? But we can still talk about the orientation and give it a negative sign once you flip it. So we put another restraint on omega, and which is omega of v1 comma v2 is equal to negative omega of v2 comma v1.
So small comment. This whole negative area business is great, but there's a simpler argument to get the exact same condition without talking about orientation separately, and then you get orientation pop up on its own.
So lambda is negative? Does it take lambda to be negative?
No, because that doesn't tell me anything about switching.
Oh, that's yes.
So the question is, suppose I had this kind of parallelogram, where this, well, I just had a parallelogram where the first vector is v1, and the second vector is also v1, or well, yeah, the second vector is also v1. Maybe. So what should the volume of this parallelogram be? What should the volume of this parallelogram be?
0.
0, because okay, it's not a parallelogram, it's just a single line. So this should be equivalent to demanding that omega of v comma v was always 0. Okay? And okay, from this that you get that if v is just v1 is linearly dependent on v2, then it's also 0. Right? So roughly if I had something like this, okay, that volume of that should also be 0. And it turns out that this condition is completely equivalent to this condition. By
Okay. So if we have
so orientation of volume is something that comes completely naturally from just the notion of volume, that there should be some orientation for it.
okay. So we have a function that's linear in each entry, and that's also alternating, which is this condition. And we can define this. So here we're in R2, and we can define this for Rn in general, right? We just have, let's say you have some higher dimensional, like parallelepiped. Okay. Okay. Let's say we have V1. This is V2, and this is V3. So in general, for omega, we can demand it so that it's linear in each entry. Suppose we have a vector space V. Let's say it's from V cross itself, let's say n times, into the real numbers. Omega of V1 up to, sorry, let's say, so we want it to be linear in each entry, right? So Vi plus lambda times W Vn is equal to omega of V1 up to Vn plus lambda times omega of V1 for all I. Okay. So this requires that it's linear in each entry, which is this.
Can you hold it up? Maybe not from the bottom, from the handle. That's probably better. Sorry. I'll be back in a minute.
Okay. And then for this condition, we still wanted to be that if you swap two of the entries, it should give you negative of that. So But this is not the most like convenient way to write this. This is actually equivalent to just saying that, let's say we have a permutation that's on like an object, and we can just permute the coordinates. So like each permutation is equivalent to like composing a bunch of swaps, right? This is swapping the ith entry and the jth entry. This is like making a bunch of swaps. And then if you notice that if you make an even number of swaps, you get positive here. If you make a odd number of swaps, you have a negative sign here, right? So to write this more neatly, we can write omega of 1 sigma 1 2. So this is just applying a permutation to the coordinates, which is the same as making a bunch of swaps. And if it's even, it gives you, so the sign of sigma is even if it's the composition of an even number of swaps, and if it's odd, then this gives you negative. Okay. And then let's make a definition. Let's define a space of all the, so this is called a n form. Let's define a the space of all k forms on a vector space V. So given a vector space V, right, omega k V, so this is equal to.
So small comment. You're making a key definition at the very bottom of the board. If you made a key definition, which you will reference later, maybe like you have that corner, which maybe you can't reach, but maybe you can try.
Okay. Definition. This is equal to the set of all functions from V cross itself and k times to the real numbers, and basically with these two properties. Let's call this 1 and 2, such that 1 and 2. Okay. And now we will try to find a. So notice that this forms a vector space.
So now you stop and ask people, why does it form a vector space? Why does this form a vector space?
Wait, it's because like you just you assign a function to a functional vectors, and then after that you just get a vector space.
Not quite. So when we say vector space, we mean we have some set where it makes sense to add stuff and multiply it by numbers, right? So these are functions that take in a bunch of vectors. But in principle, I can add these. If I take two of these functions, I add them together, I still get a new function, which has all the same properties. So there's like a vector space of these functions. So the functions themselves are vectors in the vector space. right? Because I can add these functions and I still get a function of the same type. I can multiply each function by a number and I still get a function of the same.
Okay. And there's a bunch of axioms you have to satisfy. You have to
No,
associate
forget
it.
those,
Okay.
those aren't real.
Okay.
You
Okay.
can add stuff and multiply them by numbers. And add means what it means, and multiply by numbers means what it means.
Okay.
There's nothing, no, none of this. None of this.
Okay. So this forms a vector space, which means it makes sense to find a basis for it. We're first gonna look at the case where k is equal to 1. Let me erase this. Actually, do I have a different color? I'll do this.
I should like get a extension cord for this.
Okay. So if k is equal to 1, then the set of all 1 forms on V is equal to the set of all functions, say 5, from V to R.
Linear.
Yes, linear. Yes, because we don't need to worry about this condition because there's only one input.
So what does this what would this correspond to? Linear functions on a one-dimensional vector space. They tell you the volume. What's the volume in one dimension? It's just the length of a vector, right? So then you have only one input, so it's just a simple linear function which just tells you, oh, do I have this length to the right or this length to the left?
Yes.
Yes, and so yeah, that's denoted as V dual.
It's a dual space of V. Okay. Try to talk about the dual. I'll talk about the dual basis. I'll just use this like.
What about the dual space? Do you want to say?
The dual basis.
Oh,
We needed to construct.
That's right. Yeah, go for it.
Okay. Suppose I'm gonna use like weird notation that would make sense later. X1 of 2x and is a basis for V. And then the dual basis let's denote dx1 up to dxn. So this to dxi applied to xj is equal to Kronecker delta ij. Do I need to explain this, or is xj is another element of the basis? So if they're the same, it gives you 1. If they're different, it gives you 0. And this forms a basis for the dual space. Yes, and so the goal is to use this to define a basis for the k forms in general. First, we're going to make a definition.
Right.
Sorry,
let me just give a kind of big overview, right? So we're trying to. We said that if we want to study volume, the natural way to study volume are these differential forms, which take in k vectors and output a number, and they mean something about the volume. And now we realize that one of the things they have to do is they have to be linear in each entry. So now our hope is look at stuff that takes in only one vector as input and see how can I build something like that, something that takes in k vectors and is linear in each entry, out of stuff that takes in only one vector and is linear in that. So we're now going to try and build up like the differential forms that take in k vectors out of linear functionals which take only one vector. So that's the goal of what we're trying to see. Kind of use these as building blocks for that bigger space, and see what this relationship is.
So yes. Let's try for the k equals to 2 case. Let's try to build a 2 form on V using 1 forms. So let's say omega 1 and omega 2 are 1 forms on V. And then we want to define a wedge product, like omega 1 wedge omega 2, that takes in 2 inputs from V and outputs a number. Sorry. And we're going to define this to be equal to the determinant of omega 1 V1 omega 2 V1 omega 1 V2. Okay. And I claim that this is a 2 form. So we just need to check these 2 conditions. So let's check swapping the entries. So let's just compute omega 1 wedge omega 2 applied to V2 V1. And this is equal to determinant of omega. Okay. And the only difference between this and this is that we swapped the first and second row, right? And when you swap the first 2 rows of a matrix and you take the determinant, it gives you the negative of that. It's a property of the determinant. So that's equal to negative omega 1 wedge omega 2 applied to V1 V2. And how do we see it's linear in each entry? So just compute it.
Determinant is linear in each column.
Each column and also
Right.
each row. Well, is that necessary?
You have you care that it's linear in V1, right, and V2. V1 is in the top row, right, and so V1. Okay, sorry, just go ahead.
Do I do the computation or just?
Do you remember that the determinant is linear in each row, and so V1 only enters in the top row, and omega 1 and omega 2 are each themselves linear. So if I plug in instead of V1, I plug in V1 plus some U, right? Then in the top row I get W1 V1 plus W1 U, and so forth. Okay, and then the determinant is linear. Okay, and then I get that the thing is linear in each of the entries separately. Okay, that's it. What I'm interested in, which hopefully you're going to talk about, is what does this mean geometrically?
It's the picture that. Well, this is a two form, which gives you the area of a parallelogram defined by V1 and V2.
Not just the. There's a little bit of an addition to this, right? Because you have omega 1 and omega 2, right? And these are forms over the vector space and so this vector space might be, more than 2 or 3 dimensional, right? The point is that this thing kind of projects on the subspace of defined on some subspace defined by omega 1 and omega 2. Do you see this?
Right.
Kind of? No? So let me show take this. So where should I draw a picture? I'll draw a picture somewhere here. Right? So when I have a one form omega 1, agree? It goes from my vector space into R. Do you agree? So this has, suppose I have some n-dimensional vector, right? So how large is the kernel of this thing? So suppose this is non-zero. How large is the kernel? What is the dimension of the kernel? So if this is n-dimensional, this is one-dimensional, right? How many things had to have been crushed?
One.
Well, no. If I went from n to one dimension, then n minus one dimensions had to be crushed.
Oh.
Right? So this is just from, this is, what is this called?
Rank nullity.
Rank nullity, that one. Where Axler calls it something else. Axler calls it something. Okay, so this has to be n minus 1. So this means that there's kind of one, if I have omega 1, there's, in some sense, there's like some direction, which is like a non-zero direction, and then other directions are the zero directions. That's not entirely true because there's like, I can choose this direction differently, but that's roughly the idea. So you can think of omega 1 kind of as like I'm projecting onto, I have like all these directions, and what this does is that this kind of projects a vector onto a certain line, right? So roughly speaking, omega 1 has omega 1, if I define omega 1, there is, so say in 3D, with omega 1, there is a certain preferred line direction, degree, and what omega 1 does is it takes in some arbitrary vector, projects it onto this line, and then gives you kind of the length of this vector in this line. Degree? So and then this is like this would be the output. And if we are over Rn, then this projection business actually makes sense because we have the Riesz representation theorem and so on and so forth. Okay. However, right, because we have additional structure. So this is roughly the idea, right? That this form, in some sense, you can think of it, it defines some line and it works by projecting stuff onto this line. Okay. And so what does omega 1 and omega 2 then, this wedge omega 2 kind of mean? This means that, so I have, so I'm drawing this in 3 dimensions, in like 2 dimensions in 3 dimensions, sorry, 2 form in 3 dimensions, but you can see how this would work with like m in n dimensions. So the idea is, so I have my 3-dimensional thing, and then I have my omega 1, which is going to project onto this, vectors onto this line, and say I have, I don't know, omega 2, which is going to project things, say, on this line. Do you agree? So what I now do is I take an arbitrary vector. When I plug it into omega 1, it projects itself onto this line. When I plug it into omega 2, it projects itself onto this line. So, and what I do here, it looks like I take a vector, and what is the determinant here? So I have, let's look at the rows. I take vector 1, project it onto omega 1, and then I project it onto the line given by omega 2. And I have this as one vector, and then I have vector omega 2, v2 I projected onto the omega 1 line, and then the other vector I projected onto the omega 2 line. So roughly you can think of this as I take a vector and I then project it onto this plane, right? I project the vector onto this plane, and then I compute the so I project vector v1 onto this plane, I project vector v2 onto this plane, and then I compute the volume of the parallelogram might be made by these vectors in this plane. Okay, so this is kind of the additional step that this omega stuff introduces, is that I'm not just computing the volume of the vectors v1, v2, I'm computing the volume of the vectors after I project them onto some plane, and this plane is determined by what omega 1 and omega 2 are. Okay? And so this is why this is going to be kind of a natural way to talk about volume, because hey, now I have like this, I have this three-dimensional space, but now if I have a choice of omega 1 and omega 2, I have a sense of how to compute the area of something, even if two vectors are not in the same plane, because what it does, it projects them into the same plane and then computes the area. And okay, this is going to be, yeah, this is why this is the natural definition. And so you can imagine how when we have more omegas, right, what you can do is, yeah, suppose you have more omegas, say like m of them, right? Then these m omegas, each one of them defines some sort of line. And so if I have m lines, that's going to define an m-dimensional subspace. And so I will have like a similar definition where essentially I will be projecting my vectors into this m-dimensional subspace and then just using the usual determinant to compute the volume in that subspace. Okay, maybe that made sense.
Yeah. So when we choose x1 to x as a basis for v, there's no constraint for them to be orthogonal, right? Because if not, then
yes.
the basis really depends on the choice.
Yes, let's choose them to be orthogonal for for all the cases that we usually do. We always choose orthogonal. Okay. I think in principle you don't need to, but then my kind of discussion of this projection breaks down.
Yeah.
So yeah, this projection discussion is an analogy only when you have a notion of an inner product and you choose an orthonormal basis. I agree. Okay.
But just to make it clear, so we can in principle choose them not to be orthogonal.
Yeah, why not?
Okay, and then it will completely depend on the basis we
choose. Yes. So well, which construction?
This one. So we said this dual basis is dxi.
Yeah, so this dual basis, but here I don't use the dual basis at all.
Right, but then yeah, that's true. But V1, W1 and W2 they have to be somehow written by dxi's.
Yeah, later we will do this. Yes.
Okay, yeah.
After this, okay. Eventually, once we try and compute something in coordinates, we're going to choose coordinates and compute it in coordinates. However, so far, this discussion is completely coordinate free.
Okay.
This is just kind of for later.
And then we're going to talk about like how to wedge in general like n different things. Sorry, let's use m because it's n is used. So omega. Let's say I have omega 1 up to omega m. And this takes in m vectors and outputs a number in R. So it takes in m vectors. And then we want to make it analogous to this definition. So we define it to be the determinant of this matrix. And this is sorry, let's use K. This is indeed a K form because the determinant is alternating and multilinear. And what should I erase? I'll erase this. So the claim is that if we take this dual basis and wedge it in different ways, then that gives us a basis for the K-forms on V. Oh, okay.
So
So the claim let suppose this is a tuple I1 up to IK. This is so each I, like I sub some number is a element of like 1 up to n. Subset. Notice that we only need to consider the case where, sorry, I will make a comment later. And suppose that this is in like ascending order. One. Okay. And then dxi1 wedge dxik. So the set of all k forms like this forms a basis. Sorry, that's right. This forms a basis. This is for okay.
yes. So we're claiming that we've achieved the dream. In what sense? We're saying that we want to build all of these higher order volume forms out of kind of one-dimensional ones that only tell me the length of lines, right? And so how do we say this? We introduce this way to combine a bunch of forms into one alternating one via this way of kind of projecting onto this n-dimensional subspace defined by each form and then computing the volume in there. And so here's where the choice of basis finally does come in. We're saying that given a choice of basis on V, we have an induced choice of basis on the linear functional, which gives us a choice of basis on the k-dimensional forms. So here now the basis gives you a choice. But in principle, here I could have chosen a completely non-orthonormal basis, and this whole procedure would have still gone through because the requirement is just for things to be linear and whatever, and okay, it still works.
Okay. And then we're going to check that it's linearly independent and that it spans. So proof. Part 1, we check that it's linearly independent. Okay, the notation will get a bit messy. Suppose I have a sum of m of these things multiplied by some constants.
So sorry, one thing that you're not mentioning in this whole oh wait, no, sorry, you are mentioning that the I1s are in increasing order. So roughly, you want to take these dxi's and wedge and look at all the combinations that have a different set of numbers in them. You'll want to look at I1 up to IK, where sets of numbers I1 up to IK, where I I have just all the different possible sets of numbers, and then I can just define, dxi1 up to dxik. Why do I want all different sets of numbers? Because if I had, say, dxi1 appear twice, then that would give me 0. Sorry, I'm not explaining that clearly. Just go ahead.
The notation that I used here is a bit unclear. Okay. This is a lot of indices. So for each j, we have a k tuple of ascending numbers, ij1 up to ijk. Does this make it clear? So we set it equal to 0 and show that this implies that for all j, aj is equal to 0. And
so in this case, notice that when we say that this whole thing equals to 0, this means that if I were to add all of these up, that the function that I will get will be a function that is identically 0 on any set of k vectors I plug into it.
Okay. And we're going to apply this to x I j sub j1 up to x I j sub k. Okay.
Sorry, I'm applying it to these xij.
Well, I shouldn't use j. I use a different letter.
Sorry, what is x?
The base.
Oh, x is the vector.
Xi is the basis vector, and this is like. Okay. So if the j here is equal to this j, notice that we get
so
aj.
You shouldn't use the same thing.
Yeah.
I want to be plugging in the same thing in all of them. So use like L something.
Okay. Okay. If this j is equal to L, then we get aj. Because if you look at this formula, then we plug like xi sub L1 into here, and that, yes, and then this is 1 and all the other ones are 0. And then if you look at like the second row, we get 0 here, 1 here, and 0 everywhere else. So basically, like, you only get 1 on the diagonals, and this gives you the identity matrix, and you multiply that by aj, so it gives you aj. And if j is not equal to L, then so first we have to assume that all of these are distinct, right? So if j is not equal to L, then you get at least one row of zeros, which would mean that this whole sum just gives you aj. And since we said that this is equal to 0 for anything that we plug in, this is equal to 0 for all j. So that's linearly independent.
So let me give maybe a geometric explanation of how to do this. So this dx ij1 wedge dot wedge dx ijk, what does this geometrically correspond to? So I have vector xij1, vector xij2. These are some of the like vectors in my standard basis. Okay. dxij1 is a linear map that projects onto the dxij1 direction. Maybe I should stand here because I'm gesturing so that it's on the video. So I have, right, so let's look at this one thing, right? I have dxij1, dxij2, wedge, dxijk. What is this? This means I kind of, so I'm going to show this in, say, R2. So suppose I had dx1, wedge dx2. Okay. What does this say? This say dx1, it's something that takes any vector and projects it onto x1. And dx2 takes any vector and projects it onto x2. So dx1 and dx2, I've kind of chosen this line, right? And looked at the subspace here, projected onto here, computed the volume in here. Do you agree? Okay. So this, yes. So what she's doing, so all right, there's the sum over kind of all possible distinct ways of choosing like a subspace like this, and then evaluating the volume in this subspace in my kind of m-dimensional space. And the claim is that each of these functions is not just a linear multiple of some like linear combination of some other ones. So why does this follow? This follows because what? Suppose I choose one subspace. Do you agree? Then, and so suppose I choose, sorry, here I have some number of choices of subspaces, and all of these subspaces are different subspaces that I project onto for each one of these things, because I choose the, I choose like different sets of like lines to project onto. So kind of this sum is a sum over all the possible different choices of m-dimensional subspaces in an n-dimensional space that I can project to, given this choice of bases. And so the point is that if I have this choice of subspace in this one jth term, right, that chooses some subspace with certain vectors, what I can do is I can plug into it precisely some cube in this subspace, in this subspace. And so this volume form for the right cube in the right subspace gives you volume of 1, because I mean it just computes the volume of the cube in the subspace. Okay, but then all the other subspaces, right, they are not the same as this subspace. So for all the other indices that are not J in this sum. So for them, if I plug in the right vectors for this subspace, if I plug those same vectors into the volume of another subspace, there will be some vectors that will get projected to 0. Do you agree? And so some of the vectors will be orthogonal and projected to 0. So I'll be trying to kind of compute, say, the, for example, if I, right, so if, sorry, in this example, I'm kind of taking this vector and plugging it into here and getting the volume of this parallelogram, right? But then for all the other terms are like what? The other terms are going to be dx1 wedge dx3 and dx2 wedge dx3, right? And then is there another term? Yeah, I think this is it, right? Yes. And so now suppose I plugged in this same parallelogram into dx1 wedge dx3. Well, what does dx1 wedge dx3 do? It chooses this line, and projects kinds of onto this subspace. Do you agree? So if I compute the volume of the orange parallelogram, but in this subspace, I will get 0 clearly. Do you agree? And then this is kind of this subspace, right? If I compute the volume of the orange parallelogram in this subspace, I also get 0. Do you agree? So essentially, each one of these defines some projection onto some subspace. And if what in this proof, what you do is you choose the right thing to plug into it, such that it's 1 in this subspace, but all the other subspaces, the volume of it in the other subspaces is 0. And so you get that if you plug in the right thing, you just get the coefficient of the in front of the right thing. So you see that okay, you have to get aj, and so if you want this to be 0, aj has to be 0. So that this is linearly independent. Okay. Sorry, I don't know if that helped at all.
Okay, and then we will proceed to the next part of the proof where we show that it's spans.
You know, like this picture with differential forms, that it's actually like a projection onto some subspace and like computing the volume there. I think I've said this many times, but when I first learned differential forms, I didn't understand this picture at all. And only now that I finally understand.
So part two of
Moncrief just doesn't say this at all. Like, doesn't even mention it. And it's like, what's the point? I'm not mentioning this if this is like the whole point.
So suppose omega k is a k form over v, and we want to find a linear combination of the basis vectors so that it's equal to omega k. And the claim is that if we define ai1, so this is just the coefficient in front of dxi up to, sorry, wedge dx xi, sorry. This is a coefficient in front of this. So we define this to be omega k applied to xi1 xik. So now we just need to check that omega k is equal to okay, so we sum over like all the possible like all the possible k tuples, so such that all of these numbers are in the set 1 to n, and this is ascending. So this is yes. Okay. I think it should be clear that if you plug in this onto into both sides, that it gives you that both sides are equal, right? So if you plug in this to the left side, it gives you this coefficient. And if you plug in this to the right side, so suppose that the I1s up to IK are equal. Sorry, I should use a different letter. Okay, I would write it up properly. Applied to let's say J1 up to xjk. So this would be the left side, and the right side is if this I is not equal to j, then we get 0. Right? It's the same argument as here. And if I is equal to j, then we get the identity of, it's not there anymore. But it's the determinant of the identity, which gives you this coefficient. So both sides are equal.
So roughly what this is saying physically, once again, if I have something which tells me the volume of k-dimensional objects in an n-dimensional space, then what I should do is I should just, so to specify this, all I need to do is tell you, okay, let's look at all the kind of standard k-dimensional cubes I can have, and look at what their volume is according to this form, and that will kind of tell me the volumes of any k-dimensional, right? So for example, like in this picture that I drew here, right? I'm looking at the volume of two-dimensional objects in three dimensions. So if I had some arbitrary two-dimensional form omega, to specify it, it should be enough to tell me what is the volume of this parallelogram, what is the volume of this parallelogram, and what is the volume of this parallelogram. And that should, in principle, let me figure out the volume of kind of, anything else through some non-trivial linear combination. But that's what that is just saying. The fact that, these projections onto these nice subspaces give you the whole thing. And once again, this all works even with non-orthogonal choice of basis because it just does.
Okay. Another note is that the dimension of the set of k forms over V is equal to n choose k just by choosing all the possible k tuples. You choose k numbers from n, so it's n choose k.
So this is like how many k-dimensional cubes do I have in an n-dimensional space that are distinct from each other?
Okay. And then we can
in this
talk
case,
about integrating.
Keep going. In this case, I have 3 choose 2, right? How many different distinct parallelograms do I have in a 3-dimensional space that are kind of completely distinct from each other? And that's that.
Okay. So the intuition behind this is, let's say we have some kind of surface. And let's say we want to find the volume of this. Sorry. Let's say we have omega. Such that if we given every point we have a k form omega sub p. Let's say that this is for all points in M. This is a k form. And so to find the area, the intuition is just we subdivide it into very small pieces. And let's say this is a point. Let's say we look at this squared. Then, sorry, this, it's not really a square, but if you take it small enough, you can approximate it to be one, right? And then you take these two vectors, and so the form would tell us the area of that, and then we can sum over all of the little squares, and that will like approximately give us
So
the area.
one small leap that you made here and didn't quite say is, so before we'd have a vector space and we'd have like a single form for the vector space. Now we're looking at this form on a manifold and we're allowing this form to be different at different points. So roughly, like a form tells you the volume of like space locally, and the point is now we're allowing our space to kind of stretch, and we're allowing to have different weights for space at different points in time. And so now this form is different at different points. But if I was to cut it up into small enough kind of grids, I can assume that the form is constant kind of on the little square, and then evaluate the size of the square by plugging in the vectors into the form, getting the size of the square, and then adding them. Okay, do you want to see? I can go grab a cup. Okay.
Okay. And then we're going to try to define this. How do we actually do this? So we'll define it for like a path on a manifold first. So suppose.
First, let's figure out how to find the length of a line, and then the rest will hopefully be.
This is a part of the presentation where I'm not sure about the material that I'm supposed to. This is the part of the presentation where I don't know what I'm talking about.
This is already very good. I will actually advertise this video now in Math Supported. Don't worry.
Suppose we have a path that takes in a number from 0 to 1 to our manifold. And let's say we have omega 1, a 1 form, and we want to define the integral over this path of this 1 form. And we define it to be the limit as delta goes to 0 of Is this correct?
Yes, but you have to say what the
Yes.
psi are.
So the psi is the tangent vector at ti. And it's defined to be d gamma at okay. I'm going to draw a picture first. So let's say this is a t. This is ti. This is delta I. And so gamma takes something from the t-axis to the manifold.
Use a different color for the path or something. Okay. Your diagrams are pretty good without it.
Let's say this is the path. Let's say at ti we're here. This tangent vector would be xi I. Okay, and then define. I'm not exactly sure about
So what are we doing here? So there's two important points on here. So suppose I am given some kind of curve here. So some kind of curve on my manifold. The other thing that I am given omega p, right? So I'm given some kind of element which tells me how long is a vector at kind of any point. Do you agree? So what I now do is I say, okay, if I have this line, I can choose a parametrization for this line. This is what gamma of t is. It's just a way for me to travel along this line. Okay? Then what I do is I say, okay, let's now, instead of splitting up this line, I have this very nice parametrization. So say this is from 0 to 1 degree. Now let's, instead of chopping up the line, let's chop up the parametrization into little delta t. Okay? If I chop up the parametrization into little delta t's, this will also kind of chop up the line until, into different line segments as well. Okay? So this chopping up induces this chopping. And then what I say, okay, I know that, okay, going from here to here is roughly like what? It's roughly like taking the tangent vector here, do you agree? And then multiplying it by whatever the dx here is, do you agree? And that's precisely what I have over here. I take the derivative of gamma at, so this shouldn't be just, this shouldn't be this kind of,
It's ddt.
yeah, it should be ddt because it's not. Yes. I mean, it's the same, but it's not the same.
This is not correct.
Yes, at ti, and then yes. So I take the derivative of gamma, right? I get this tangent vector, and then I multiply it by delta I, right? But roughly speaking, instead of, yeah, that's right. So, and then, so I get this vector multiplied by delta I, and so I get a vector now kind of on here, right? And hopefully that this is small enough such that going from here to here is roughly but as going along this tangent vector. Then I use the volume form to compute what is the length of this vector according to my volume form. Okay? And then I just add it all up and then take a limit as these deltas get smaller. So this is all this is. Okay? But now you can, yeah, right. But yeah, okay, go ahead. So does this procedure make sense? So now there's an important point here, right? So this curve, right? It does not depend on what? On what?
How fast you travel.
The parametrization, right? So because in principle, this choice of parametrization was arbitrary, and this definition, I'm trying to give you a definition to define the length of this curve according to volume form omega, right? That's what I'm trying to do. And here I just told you, oh, let's choose a particular way to travel along this curve, and that really features in our definition. So we made this choice of parametrization, and hopefully this sum is not going to depend on this choice of parametrization. It doesn't. Well, I don't know if you will show it, maybe don't show it, but the point is it doesn't. You can show that if you chose a different parametrization, you'll get the same thing after doing some change of variables. And so this really defines the length of this curve according to this volume form, right? So what did we see? We saw that we had this one form, right? What does this one form do? This one form kind of at every point picks a line and like projects on it and says that that's the length of lines according to this projection. So this kind of defines the length of lines at every point. And we now saw that I can now use this to measure the length of some potentially curved object on my manifold. Okay? By doing this kind of procedure of like taking this line, chopping it up, and then using tangent vectors and to approximate the line, and then computing the length according to the volume form. Okay, and now we're going to, well, I don't know what you're doing in what order, but eventually we'll do this for like an n-dimensional surface. We'll have an M form in a maybe larger space. I'll have some surface, and then I will do a similar procedure. But okay, go ahead.
Yes. Okay. We're gonna repeat the same procedure for like
Actually,
something in
can
Rn.
you maybe write this down as an integral now? Like as a proper integral from 0 to 1 of t. Or you should write somewhere where you have less space, so you can write even smaller than that.
Okay.
Like literally, yeah, just write to the right of it. That's already better.
One. I'm gonna apply. Is this correct? Sorry. No. Wait. Is this correct or?
That. So the pullback. So the one thing you're forgetting is that the volume form depends on the point. So it's defined at.
Oh, it's sub gamma.
Yes, so sub gamma of t.
Okay.
And maybe let's write this kind of more clearly. That here I'm plugging in ddt of gamma of t, like this. So I take ddt of gamma of t, I get a vector. I plug it into my volume form at the appropriate point, and then I integrate it with respect to dt. Okay? And this is very suggestive. This is very suggestive, right? What did I do? I took kind of I took a vector here, do you agree? Pushed it forward to a vector here, and then just plugged it into the form and integrated that. So hopefully for n dimensions, for an m dimensional thing, we do the same thing, right? I will have some manifold. I will have some coordinate chart for that manifold. Then I looked at the stuff in the coordinates. In the coordinates, I have x, y, z directions, which are very simple, right? And I'll kind of plug in a parallelogram or a cube in my directions, see what it gets mapped to, what kind of cube it gets mapped to here, and then evaluate the volume using the form of the cube once it gets mapped to here, and then add up over the cubes in the coordinate chart. Okay, you will now explain. Or maybe you'll explain something else, I don't know. Sorry, I'm putting expectations on you, which are unfair.
Okay. And then I would.
But there's one expectation of turning the laptop. That's
Oh,
definitely
true. Okay. And then we can use this to define integrating in like RK.
And also, yeah, see how we chose before this notation of dxi to mean a one point, right? Remember how when you were writing integration, like in high school, you're writing dx1, dx2, whatever. It's the same idea. It's just that now we have a meaning for what these dxi mean, more rigorous.
Okay. So let's say we have omega k. Depending on, I guess, let's say x is a point. So in RK, x is an RK. And then for each given x, we have a k form. So omega k at x is a k form. And let's say we have some volume in like RK. Let's say this is This is the volume that we're trying to integrate over. Because we know that did I just erase it? Oh. We know that linear combinations of this forms a basis for the K-forms. Yes. So because here the dimension is equal to, like, the dimension of the form is equal to the dimension of the space that we're in. We only have one choice of this, like, K tuple, because we're like all of these numbers are chosen from like 1 up to n, right? But in this case, n is equal to k, so we have no choice. So we can rewrite omega k at x to be some function of x. So phi is from rk to r. Phi times dx1 wedge all the way up to dxk. And we require phi to be smooth. Now we can define the integral of this form over this volume.
Sorry, so just to make a point that if I have a k volume form in a k-dimensional space, it doesn't have any sum. It's just dx1 up to dxk, because there's only one cube that I can kind of fit into one k-dimensional cube in a k-dimensional space that I can fit. Sorry, I'm just explaining why this is a one-dimensional.
Yes, that's what I was explaining.
Oh, I'm sorry. I wasn't listening.
We integrate over the volume d of this form. And we define it to be this should be an integral that, like, we know how to do. Yeah. Okay. Okay. And then is the reason that we define a pullback so that we can do this in a manifold and not just.
Yes. So the point of a pullback is, so here I have a k-dimensional form and a k-dimensional space, right? In principle, in this case, I had a one-dimensional line in a multi-dimensional space. Do you agree? So I need to kind of restrict this back onto something one-dimensional, and I need to pull this back onto coordinates which are one-dimensional, get a form on the coordinates, and then integrate the form on the coordinates. Because that's what we kind of did. We took the form on the manifold, turned it into a form on my coordinates, and then integrated it in coordinates. Right? Like I can only integrate a k-dimensional thing over a k-dimensional surface. If I have a k-dimensional thing and a higher n-dimensional thing, I need to first restrict to the surface and then integrate over the surface. And that's what this pullback helps me. It helps me restrict myself to the surface.
Okay. So then we'll define what a pullback is.
Right, so now the goal of what we want to do, we understand how to integrate a k-dimensional thing in a k-dimensional space. Now, how do we, if I had a k-dimensional volume in an n-dimensional space, how do I, given a k-dimensional surface in a higher dimensional space, how do I now integrate that? Find the volume of that. Okay. And for this, we need the pullback.
Yes.
I think it's one word.
Oh, it's one. Oh.
I think so.
Suppose we have a function from m to n where m and n are two smooth manifolds. and let's say we have omega, a K form on N. And we define F star
Yes.
with this. So if we apply F star to omega, it's equal to omega applied to F of psi 1 up to F of psi k.
It's df, right?
Yeah.
Well, the thing you want to be plugging in has to be sorry.
These are elements of N. F is.
Oh, sorry. This is the point of.
Yeah, this is a point. Sorry.
Which things are vectors and which things are points? No. If I plug in a bunch of them, they should be.
The k vectors in M.
Yeah, so k vectors
So
in
at
M,
a
M is a
point.
manifold. So first of all, you need to specify the point, and the other thing is not F. So F does not map vectors. F maps points. What you want is you want df to be mapping the vectors, right? Because the thing you plug into this volume form are tangent vectors. So okay, let's draw a picture. I have one manifold n. So actually, I'll make it simple. I have one manifold n, which is, let's say, flat coordinates, which is usually the case you consider. And then I have some, curved surface somewhere else. Okay? And I have a map F here. Okay? And on here, suppose I have a volume form defined, right? Which, say it's whatever dimensionality form. And it takes in tangent vectors. So at point P, it takes in the tangent vectors here as input and tells you what the volume of like a parallelogram made up of these tangent vectors is. Okay? But now I want to do is I want, using this function, to turn a form on here into a form on here. Okay? How do I do this? Well, what I do is I take what I do is I take the same form. Instead of evaluating at point P, so I want to turn this form into a form here. So it has to be evaluated at a point here and take in tangent vectors at this point. Do you agree? How do I do this? So suppose this point gets mapped to here. So this is point X, and then this point will be f of X. So f pullback of omega evaluated at point X. And suppose I plug in vectors, okay, some vector psi 1 dot 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 psi, which is the k form or what? K. Psi k. So it takes in. Okay, so this is now going to be a form. F pullback of omega is going to be a form on here, which I define in. So this is almost correct. So let me remove this. This is going to be at point X. I'm going to take this point, map it here to f of x. So I'm going to be evaluating this form at f of x. And what I will do now is, okay, I have these tangent vectors here. Do you agree? These tangent vectors, how do they get mapped under f into tangent vectors here? Well, by the Jacobian. Remember, we talked about this at the very beginning, right? This vector by the Jacobian is going to be mapped to df of this one, right? So you have df psi 1 up to df psi k that you put into it. So it's roughly, you had this parallelogram. F kind of maps it to a different parallelogram here. And then I just evaluate the volume of this parallelogram as the volume of this skewed parallelogram after it gets mapped by F according to this volume form. Right? And so now I took this form and I kind of pulled it back onto this space. Do you see? Okay. And so now this is going to be very helpful because, okay, at the end of the day, what I'm going to do, I'm going to have some manifold and I'm going to give it coordinates. Do you agree? And these coordinates are going to be nice flat coordinates, you know, dx1, dx2, dxn, where all of this stuff is very, very easy. And I will get that I kind of, I'll be able to integrate this volume form via, so I'll be able to reduce an integral of this volume form over some curved surface as an integral of something in just flat coordinates using this pullback. And well, actually, I will define it to be this way. And this is going to be roughly the same idea that we had here, right? Here I had some line, right? I gave it a parametrization, so I gave it some coordinates, chopped stuff up in coordinates, and then that gave me a chopping up here, and then integrated this chopping up using coordinates. But this was one dimensional. What we're going to do here using this pullback is I'm going to have a form, I'm going to pull it back, I'm going to parameterize my surface using some coordinates. I'm going to, using these coordinates, I'm going to pull the form back, then chop stuff up into little squares over here, right? Those little squares are going to give me some kind of chopping up into little squares over here. And then I'll see, okay, how does this get mapped to a square here? And the area of this square is going to be given by omega p, and I'm just going to add that. Okay? And over here, this is just going to be each of these squares will just have a weighting of omega f of p. Do you agree? Roughly, with like the vectors plugged into it. Yes, okay. Sorry. And so then I will be able to just integrate this as an integral from dx1 to dxn. Okay. Sorry, yes. So this is important because f does not map vectors. F maps a point here to a point here, and then df maps the tangent vectors. Right? So this has to be df applied to.
Okay. And
So does this clear up what you're
df at x, right?
Yeah, df at x, correct. I guess
at
our
x,
notation, we put the x here, or at least in the notation
Here?
I put the x there, yes, and then it's just the derivative of f at point x. Maybe that's confusing because
Beerstone
sometimes-
writes the vectors here and the point here.
do whatever you want. I don't care.
Okay, I'll
Because
just.
yeah, sometimes
Right,
d sub x people mean as the derivative in the x direction or something. Okay. There's as much notation as there are people in the world. Okay. I will. Yeah, we really need to solve this. This should have enough battery to. We're close to the end.
Okay. Okay, and because of the pullback, we can define how to integrate on this manifold, right?
Yes.
So let's say we have some. Let's say this is. Let's use this one. Okay. This is equal to. Right. I'm not exactly sure what Arnold means by this.
What letter is that? Is that a D?
D.
And this is D comma F.
I think you wrote this. Like
D comma F
which is
comma what? Comma what?
comma F comma orientation. That's
Oh,
I
comma
don't-
orientation. Yeah. So roughly what he's saying is, I think he's just defining saying that a coordinate chart is like a coordinate chart is a map F with a choice of orientation and the choice of D, which is like what does it cover. What does the coordinate chart cover?
Is he defining this to be this or this to be?
He's defining this to be this. So the integral of omega over some surface D with coordinates f is just the. Oh, yeah. Right, sorry. In his case, D is my region in coordinates. This is D.
Oh, sorry,
And
okay.
then what it gets mapped to is the thing I'm integrating over. So f of D. So I have some region in coordinates, which is simple. My coordinates get mapped to some curved surface with omega. And yeah, so he just defines the integral of omega over some f of D to be just the integral of the pullback of omega under f star with respect to over D in like flat coordinates.
Wait, so is F like a chart?
Yes,
And-
f is like a chart.
Oh, and this is like our.
No, other way around. You want you want this to be Rn, and this to be the manifold, right? So this is how you will do it in the end. I have a manifold. I have some coordinates for it. Instead of doing this complicated thing in the manifold, I will just pull this back to a form in coordinates where I just kind of have a weighting for what each little square, how large each little square here is, according to both the form and how the square gets deformed as I map it. Okay?
Wait, sorry. Then how does this define? Because F star applied to omega is
Is f star applied to omega? This was a k form here. This becomes a k form over r. This becomes an n form over Rn. We had an n form here. This becomes an n form over Rn. Do you agree?
wait, but this is a vector in Rn,
Yes.
and this is a vector in N.
This is
A
a tangent vector at point f of x and n.
Yeah.
Correct.
So we don't know how to integrate this.
No. This thing. So this thing is over here, right? So f
wait,
star omega takes as input point x and vectors in Rn, which we
Yes,
know
okay.
how to integrate. This will in fact just be some function, I don't know, some a of x times d psi 1 wedge dot 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 wedge d psi k. Right? This will end up having this form. Do you agree?
Yes.
And this I know how to integrate. Right? So I know how to integrate this.
Oh yes. Okay.
And
yes.
this is the integral I want to define.
Yes. Okay.
I will write up maybe one single simple exercise at the end where you're just going to compute the volume of the sphere. And you hopefully know what in 3 dimensions. And hopefully you know what the answer is supposed to, not the volume, the area of the surface area of a sphere of a 2-dimensional sphere in 3 dimensions. And hopefully you know what the answer to that is. And it's a nice calculation. I think it will be a good example. Okay, do you have more things to say?
I mean, I didn't really have time to prepare more.
This is actually perfect. I think this is a good place to start. Okay. Yes. Okay. Do you have questions?